So thanks, guys, for the opportunity to have a bit of chat about this, a bit of work in progress. But yeah, I just wanted to introduce the problem, and then Bonnie will talk a little bit about how we're sort of addressing, yeah, the issue of bushfire suppression, modelling bushfire suppression effectiveness, I guess. So jump straight in. So the background of this is that not just Department of Environment, Land, Water and Planning, but other agencies like the Country Fire Authority in Victoria and Fire Rescue Victoria as well, plus Emergency Management Victoria. So there's a whole range of different agencies have some responsibilities for managing bushfire across public and private land. And so they sort of dispatch or discharge, I guess, their responsibilities through a range of different actions. It might be declaring a total fire ban day, or it might be something to do with fuel management in terms of reducing the fuel loads to potentially modify fire spread through a forest area or on a roadside, or it might be through compliance or education activities. But one of the main sort of ways they discharge their responsibilities is actually setting up for a bad fire day, so the preparedness side of things, and then actually responding resources to a fire. And on a lesser day, like on a mild weather day, then a lot of these things just automatically happen to some degree. At least for the Country Fire Authority, they will dispatch 3 fire trucks as a typical response. And we have some other treaties in place around some of our aircraft deployment as well. But on those more complex days where you start to get hotter conditions or more windy conditions, or maybe you've got mixed fuel types, you've got some forest and grass in combination where a fire might start and spread, or you've got lots of assets in play, then it becomes a little bit more complex to think about what combinations of resources, or combinations is probably the right word, of do we actually send to the fire. And so a duty officer, which most agencies will have that responsibility to actually determine beyond the basic triggered resources, the 3 fire trucks or the aircraft, or what else might they send. And so there's sort of 2 components to this. It's the setup to the bad day. So what sort of resources should we have in place in the landscape, and where should they be located, and what type of resources should they be? And so there's normally 2 or 3 days in advance we'll have a bit of a conversation around what that could look like. And then there's actually the response itself. And so as a duty officer myself, or an incident controller, I might be asking the question, should I be sending an extra bulldozer to this fire, or is that overkill? I don't need to do that. Or should I actually be sending, what sort of aircraft types? So should I be sending helicopters or airplanes to the fire? Do I have enough firefighters to actually hold the fire? So you might be able to put the dozer around and contain the fire to a point, but then the spot's over. So I need some resources there to hold the fire in an area of interest. And what if I actually have 2 starts that I've only got finite resources? Where should I send my resources? Which fire? So there's a lot of complexity here. And as a duty officer, this is just the response to the fire bit. I've also got to think about warnings and advice, and potentially setting up some incident management team if it's not already in place. So there's a lot going on. And I guess what we're trying to do with this project is actually start to say, well, is there a smarter way, given the technology we've got today in today's world, to actually start to optimize optimize our resource response to some of these more complex fire events. So in terms of the factors here, that we're sort of interested in thinking about, we want to really start to say, is there a modelling capacity or way to actually capture all these different resource combinations and say, how do they influence the fire spread or fire containment within a certain amount of time? It needs to take into account things like fire weather and the dryness of the landscape. In terms of the spatial scope, we've started reasonably contained just the Bowen Southwest area, which is still a pretty big area, but that sort of covers from Geelong all the way across to Portland in the down near the Victorian South Australian border. And in terms of the time horizon, you could pick different times, but we've sort of picked a sort of 8 to 10 hour period, or a little bit longer, sort of the first shift. So your fire starts, and we're going to send resources, and they're going to work until I guess there's some sort of changeover in shift. So it's really the first 10, 12, maybe 16 hours of the firefight. So in terms of the modelling approach that we've sort of looked at, I mean, we've picked a Bayesian approach for a number of reasons. One for us is actually a lot of uncertainty when a fire is reported from, and often it's through the public. They'll report a smoke sighting somewhere, and we know based on historical reporting of fires, it's average 3 kilometres from the actual location, and in the private land, often it may be just an intersection. In the forested areas, if we've got our fire towers up, it's sometimes a little bit tighter than that, but there's definitely a lot of uncertainty there. You guys would know with the forecast weather, there's actually lots of uncertainties around that, and in terms of landscape dryness, so we need to try and map how dry the landscape is or not. So we need to take into account these factors and say, well, we're not 100% sure exactly what the state of the world right now, but we've got an idea. Let's start with that and have some variation around that. We also have some data on suppression effectiveness, but we've also got lots of gaps, and particularly around how different combinations of resources actually work together and are more or less effective. And the other thing we've got in it, probably to offset that a little bit, we've actually got a lot of industry experience. And if you think about the large fires we've had over the last 20-year period, we've actually had some of the bigger fires in our history as a nation. So, but beyond that, we actually attend thousands of fires between all the agencies, the fire agencies in Victoria every year. So there's a really deep knowledge there of some of these things, even if it's not necessarily written down. So,
Tim, we'll have to cut soon to the video.
All right, thank you. All right, I'll skip through this a bit. But look, effectively, we've drafted up a basic model, and it's got aircraft. We've got forest construction rates, and we've got some grass construction rates, and we really want to get it down to that probability of success there. And as I say, one of the key things was this idea of putting in some sort of fire simulation to capture some of those variabilities in the likely spread potential of a fire. And we're using the Phoenix Rapid Fire model to do that. And we're going to run it in an ensemble approach, which is a little bit different to how we've done it in the past in Victoria. So we're going to run lots and lots of iterations and variations of weather and fuel dryness, and that will start to interact with our resource probability sort of outcomes based on what we send to the fire.
Okay, thanks for that project background, Tim. Now I'm just going to give a really quick overview of how we elicited judgments from our expert participants over a series of workshops. So for all our workshops, we used an iterative process to elicit judgments from people based on the Delphi method. So basically, it's a process that allows our experts to give anonymous forecasts or judgments, provide reasons behind their judgments, which are circulated to other experts, and then they can give their judgments again. Our first 2 workshops were aimed at building model structure. So first in round 1, we asked people to do this by themselves, in this case, create their own basic conceptual model. So to brainstorm and develop competing models of the system, different stories of cause and effect. And we asked everyone to do this by themselves because we didn't want them to be too influenced by everyone else to begin with. Then we came together during discussion and talked through each of the models, and then we had some more. Then we had some quiet time in round 2, which gave everyone an opportunity to have a think about the things that we discussed and make any changes to their model in light of that discussion. So we used the BARD platform for building our models, our model structure, which was developed by Anne Nicholson and her team at Monash Uni. Sorry, probably many of you would be very familiar with Anne, I'm sure. And so Ross Pearson in our workshop gave a quick BARD overview and some training to everybody. So, for example, how to add in variables and arrange preferred variables into a model, adding arcs and arrows between nodes. And so in the workshop, or before the workshop, we assigned everyone an anonymous avatar. Australian animals, as you can see here. Each person built their own model, the structure only. Then we discussed each of the candidate models systematically via the BARD platform. So people could do this in real time over Zoom, with discussion being expertly captured and summarised into the platform by the most excellent and overqualified scribe, Kate Parkins. Thanks, Kate. And participants could anonymously type in their own comments under each model into BARD directly if they preferred. Then Tim and his team went away and consolidated this information into a single model. And we found BARD to be a really useful platform for collaboratively building the model structure. So once we'd settled on a single model structure, we started tackling the parameterization step, so we could populate some of the CPTs that we didn't have data for. So rather than eliciting probabilities directly for the CPTs, we elicited the quantities of interest, which we later converted to probabilities. So we used the 4-point methods here, which allows people to express their uncertainty around their quantity judgment. So we gave people a survey to fill out ahead of the main parameterization workshop, which contained a heap of questions like this one. Please estimate the average construction rate in meters per hour of a single D4 dozer in light bush. And then we asked for an interval within which they have a certain level of confidence contains the true value. So in this case, the actual average construction rate of a particular piece of machinery under given conditions. So specifically, we ask this over 4 steps, 4-step method. The first step being realistically, what is the lowest plausible value might be? What's the highest plausible value? What's your best estimate of the construction rate in this case? And how confident are you that the interval you've created from lowest to highest captures the true value? Again, we use an iterative Delphi-style method for eliciting judgments. This one's the IDEA protocol, stands for investigate, discuss, estimate, and aggregate. So basically, experts give their first anonymous judgments via the survey, provide reasons behind their judgments, which are circulated to the other participants. Then we come together as a group in the workshop and discuss these judgments, focusing on differences of opinion, and participants are given the opportunity in round 2 to revise these judgments in light of the discussion. And then we go away and combine or aggregate their judgments. So that was a quick overview of the process, and the survey also contained key definitions just to make sure everybody shared a common understanding of these terms. We spent a bit of time, not too much time, clarifying these further in the workshop as well. So here's a quick example of one of the question blocks from our survey. We've run about 3 or 4 surveys and accompanying workshops. So this was one of our first ones. So here we're asking our experts to consider a lot of different conditions at the same time, which we all know is really, really hard to do, but necessary for the model. So for example, here we're asking about the average construction rate of a single D4 dozer under a bunch of different interacting conditions. So for example, under background, tree hazard conditions, and we gave them the definition there. When you don't have any excavators present, when you have hardly any slope to deal with, little or no impediments to construction, and then we go through different combinations of these states of variables. We also asked a few questions about how the construction rate might change when we have more machines and more slope to deal with. Then we asked our poor experts to do it all again, but this time estimating construction rates of D6 dozers, different types of dozers, and Rayco crews, among other things. So here's an example of the sorts of plots and summary info that we discussed in our workshop group. So after everybody's already given their round 1 judgments. So this is a plot summarising these round 1 judgments of the construction rate of a D4 dozer, a single D4 dozer, given background tree hazard conditions, so with no hazardous trees or few hazardous trees, and under different levels of impediments, impediments being impediments to construction such as rockiness or dense bush, things that will slow down a dozer. So we have the construction rate here, impediments along the bottom, and the symbols indicate the presence of excavators, another variable here. Usually excavators are usually used for clearing hazardous trees. Anyway, probably too much information, but anyway, so we systematically discussed each of these plots like these, and people could then go away and revise their judgments in light of this discussion. So we sent them personalised Qualtrics survey links that contained their round 1 answers, which they could simply update if they wanted to. Once we'd been through that process, we were left with a bunch of 4-point judgments, which we aggregated and then converted to a form compatible with CPTs, with conditional probability tables. So to do this, we took participants' upper and lower bound estimates and readjusted them to be 100% intervals, so theoretically the minimum and maximum values. We used a triangular distribution to simulate 1,000 values for construction rate. So most values in the simulation should be near the best estimate, and nothing should be outside the upper and lower values. Then we just count up all the simulations that fit into each discretization, and that gives us the probability distribution. Simple as that. So I realise that's a bit of a knotty slide to end with, but I'll leave it there and handball back to Tim, and he can hopefully field any of your questions, and feel free to email me if you have any questions about our elicitation process. Okay, thanks everyone.
Yeah, look, we're still, as I say, it's a work in progress. We really got a couple of extra workshops to run to fill it in, and then we're going to try and test it, assuming we have some bushfires later this year in February. And how we're going to use this is actually have a series of output maps, so it'll try and take into account different ignition locations, and you'll actually try and pick the best, I guess, the most appropriate map based on the ignition location. So yeah, and there's lots more you can do once you start going down in these little rabbit holes around timeframes and resource combinations we haven't even thought about yet. So thanks for the opportunity to present.